Today we'll answer the very important science question, what is the best feature of the dog and why is it their eternally wet nose? Stay tuned. The field of neuroscience has been narrowing down to focus on just a few animal models. But the animal kingdom is so much bigger than just rats and mice and worms. This is neuroscience beyond the mouse. So I'm going to come out swinging with the neuroanatomy and drop the word rhinarium early on. The rhinarium is that little bit of hairless skin that surrounds the nostrils of some mammals. And just to be clear, rhinarium is not just a fancy word for nose, even though many scientists, myself included, sometimes use longer words than necessary. The rhinarium is so much not a nose that actually humans and some primates don't even have them. But dogs and cats, on the other hand, have very pronounced rhinaria. The rhinarium is a sense organ. It functions like an accessory olfactory organ that can basically detect the presence of chemicals in the air, like food particles or pheromones. It also works a little bit like a somatosensory organ or a touch organ, which you'll notice when you watch dogs poke around new places with their snouts. In this 2020 study, published in Scientific Reports called Dogs Can Sense Weak Thermal Radiation, the researchers suggest the rhinarium is also a temperature sensing organ as well. And they show some brain scanning data. Now, figure 1 deserves some kind of science picture award. This image shows the surface temperatures of a golden retriever's face. The warmest parts, clocking in at about 38 degrees Celsius, are really close to mammalian body temperature, and this is what you'd find in the mouth and around the eyes. And this makes total sense, since these are the areas that aren't covered by fur, which actually functions as an insulator. At the other end of the body temperature spectrum is the coldest part of the face, and also the most boopable part of the whole animal, the tip of the nose. And at 22 degrees Celsius, around 70 Fahrenheit, the nose is right around room temperature. Oh wait, here's the award that this image should win. Most unnecessary scale bar in science, provided just in case you forget how big a dog is. The theory is that dogs, using their much cooler rhinaria, are able to sense very subtle changes in temperature, such as a gentle warm breeze of air. The skin on their rhinaria receive very rich innervation by sensory neurons, and the authors suggest that temperature is one of those important environmental cues that dogs really care about. Now, this idea stems from observations seen elsewhere in nature, in other animals that are like completely antithetical to the ideas of dogs, pit vipers. The most well-known pit viper, at least in America, is the rattlesnake. These animals hunt in part by using very specialized temperature detection organs called the pit organ, which is found right in their face. The pit organ is actually separate from the nostrils, and it turns out that these pit organs are so sensitive that they can detect temperature changes as subtle as half a degree, allowing them to locate their prey even in the darkness. Now, the pit organ could be a whole nother episode on its own, so I'll save that discussion for another time. Okay, back to mammals. Now, how did these dogs get selected for this study? The answer is actually my favorite line in this entire publication. They were privately owned pets and put to our disposal without economic compensation. And I love this sentence so much because syntactically it's unclear whether it was the owners or the pets who actually did not get any compensation. Regardless, the study indicated that all of the dogs recruited for the study were mesatecephalic, which is just fancy dog breeder talk for medium head length. Now, this criteria actually rules out several breeds, including the flat-faced pugs and bulldogs, and it also rules out those long-snouted terriers and German shepherds. This variable may actually be significant since the volume of the nasal cavity may have an impact on how well these animals perform on some kinds of olfactory-related tests. Now, there were 2 different sets of dogs tested in 2 different locations on 2 different kinds of tasks. The first set of experiments was a behavioral test. We had 3 good boys, Kevin, Delphi, and Charlie, and they were trained to walk down one of 2 hallways. Wafting down the hallways towards the dogs were 2 different temperatures of air, either ambient room temperature or warm air. And at the very end of the hallway, there was a little food reward, which the dog could access by pushing the little panel. Now, when testing begins, the animals were free to walk down either of those two hallways. The goal was to train the animals to prefer the warm air hallway. So they would walk down the warm air hallway, get to the end, push the panel aside, and get their food reward. But if they walked down the ambient temperature hallway, they would find that they were no longer able to access a food reward, and I hope the experimenters felt bad. All three of these dogs very quickly learned that warm air meant snack time, and those data are summarized in Table 1. Now, the second set of experiments were a little bit tougher to conduct. It requires that the dogs lay down in a functional magnetic resonance imaging scanner, or an fMRI machine. The fMRI is a clinical imaging tool that is often used in the hospital. It's very useful for detecting changes in features of the brain, such as how much those blood vessels are dilating at any given moment. The best part about the fMRI is that it's completely painless, and it can be done while the subject or the participant is engaged in some kind of task. So even though the fMRI is painless, it doesn't mean that it's easy. For one, the animal has to stay completely still. After all, the scanner is just capturing images, just like a camera. And you can imagine how difficult it is to get a crisp, sharp picture that's not blurry if your subject is wiggling around all the time. Also, the machine is really loud, and this can be very distressing for the dogs. So they had to be trained specifically for these unusual conditions. Once these dogs have been trained to sit in the scanner, the experimenters exposed them to either ambient air or warm air. Now, in their supplemental figures, they actually show the air-blowing device. And if this wood, glass, and styrofoam design looks super low-tech, it actually has to be, by design. One issue with the fMRI is that it uses a giant electromagnet. In this particular experiment, they used a 3 Tesla magnet, which has the equivalent power of 30,000 Gauss. Because nobody really knows what a Tesla or what a Gauss feels like, let me put that into some context. A cute refrigerator magnet, like this one that says, "Hello from the otter side," is about 100 Gauss. A junkyard magnet, like one used to lift a car, is about 10,000 Gauss, or 1 Tesla. So when you see that they used a 3 Tesla magnet, you know they really mean business. Now, these fMRI magnets are so powerful that if you bring your cell phone or your wallet into one of these rooms, the strips may get demagnetized. People have been injured, sometimes even fatally, after being hit by metallic objects that have been accelerated by the strength of these magnetic fields. And now, with all the metallic objects cleared out of the room, they brought in the dogs one at a time, put them in the scanner, and then presented them with either ambient temperature air or warm air. The fMRI then scanned their brain for changes in blood oxygenation level, and they found that there was a specific part of these animals' brains that responded to the warm air, but not the ambient air. It was the left somatosensory association cortex. The somatosensory association cortex helps contribute to our understanding of complex physical sensations. For example, we could pick up 2 different round objects, and using circuits including the somatosensory association cortex, we could tell that one of them might be a baseball and the other one might be an apple. Given the role of this part of the brain in humans, it makes sense that in dogs it carries out a similar function. So here's one little piece of information that was never cleared up in the publication. They spent quite a bit of time talking about the rhinarium and its functions, but they never clearly associated this temperature sensing function with the rhinarium. In fact, I wonder if you could just cover up their little wet doggy noses and then see if they could perform those behavioral tasks, put them in the scanner, and see no difference in the somatosensory cortex. This would really give us a good clue that it's the rhinarium that's responsible for these features, rather than just the skin around their face. Regardless, I find any study involving dogs and fMRI really fun. Plus, they're one step closer to solving the dogunculus, which I think is on every scientist's mind at all times. Thanks for joining me here today on Neuroscience Beyond the Mouse. Leave a comment below and tell me all about your favorite dog's rhinarium.